Chris, please.
Okay, thanks very much. Let me share the screen. Oh, sorry, hang on. I made a mistake. Let me try that again.
Looks taking time.
Yeah, sorry. Okay, let me try one more.
Okay, we see your iPad screen now.
Okay, sorry about the delay. Okay, so yeah, thanks again for the invitation to talk. So yeah, I'm not going to talk about anything particularly sort of deep or grand, but it's just sort of a nice construction that I think is relatively easy to explain. It does not require a lot of complicated mathematical machinery. And it's this idea of getting a sort of algebraic structure out of what is really quite sort of minimal hypotheses and maybe some applications that you can do with that. So in particular, I'm going to talk about these things called Delone sets. So let me first explain what these are. So just to set notation, so we have a point in RD, if you want, just think of the plane, and you just set some positive number, and this BXR is going to be the ball centered at X with radius R. And we're going to actually have two R's. We're going to have a little r and a big R. And we're going to look at a discrete and infinite set, which I'll call this curly L. And we're going to, and this curly L is a little r, big R Delone set if two criterion are satisfied. Firstly, if I look at the intersection of this L with the smaller ball, so the ball of radius small r, and I look, and this vertical lines means just the amount of elements in that set, and that should be no bigger than 1. So in particular, this is telling you that this L has no, so this is true, should be true for any X. So it's telling you that no 2 points within L are sort of arbitrarily closely clustered together. There's always some amount of spacing between points. And I also asked that the intersection with the ball of radius big R should be at least 1. So yeah, there's no 2 points that are too close together, but also there's, if I get a ball big enough, then I will always find some other point, which is not too far away. So no, there's nothing too close, nothing too far away. So this is sort of the main hypothesis that we're going to have. And so in particular, sort of a working idea is that if you think about a material and it's sort of its atomic configuration, at least at low temperatures, right, you would expect that the atomic structure or the atomic layout of this material should roughly be one of these Delone sets. Okay, there's maybe the question, okay, it's not really, materials are not infinite, but okay, assuming some, if you'll allow me to also assume some kind of infinite condition as well. Okay, so that's just the definition. Let me just give a couple of examples. So, you know, obviously if I have one of these sort of crystalline-like materials where you have a sort of a nice lattice structure, then this is clearly an example. So crystalline materials are Delone sets, but also sort of more amorphous or random type materials. So this picture here is, I think, of glass. So, you know, points are not arranged in any sort of rigid or periodic fashion, but at the very least, you can say there's still a minimum distance and a minimum and maximum distance between points. So we can also consider a slightly more mathematical example if I zoom in. So this is a so-called Penrose tiling. So maybe people have heard of it. It's an aperiodic tiling of the plane. So we sort of build it out of just these basic shapes, and there's certain rules that you stick things together, and you can fill out the plane in in a way that it's actually aperiodic. So in particular, you could build a Delone set by taking all the vertices, or maybe just points from the middle or something like that. That would give you another Delone set. And down here, I've got the diffraction pattern of a so-called quasi-crystal, which is sort of neither crystalline nor amorphous. It's somewhere in between. I mean, it's not periodic, but there's also a lot of internal structure there. So these were discovered in the 80s. And maybe you're thinking that these two figures look similar. I mean, I would agree with you if you thought that. But the point is that, there are many different examples that you can consider. Okay, so now what I want to do is, so again, the title of the talk was building something from nothing. So nothing is in some sense the Delone set, and now we're going to try and build something. So first, what we want to do is we want to talk about some notion of topology and convergence for Delone sets. And there's actually a few different types of topologies you could put on a Delone set, but I'm going to just talk about one. So first, okay, we just establish notation. We just call this del little r big R to just be the set of Delone sets. And yeah, we want to have some notion of convergence of these sets. So, and the way that I'm going to do it is, okay, so, your Delone set is a collection of points. So at each point, I'm just going to think of them as putting a little point measure, or if you like, a little Dirac point measure on each of these points. So in particular, the way that I can think about this is if I have a continuous function that's compactly supported or just has closed bounded support, then I get this functional. So for every function, I get a real number just by evaluating the function on the point of the lattice and then just summing it up. And because this function has compact support, it has bounded support, this will always converge. So then what I can do is I can equip from this functional, I can then just pull back the topology using the weak star topology of this functional. So what that means is that we say that a sequence of Delone sets will converge to some other Delone set L if for all compactly supported continuous functions, I get this convergence of these measures where now this is just convergence in the real numbers. So it's you can make sense of it quite easily. And okay, just a relatively basic proposition, which is just due to Bellissard actually. So this basic construction that I'm going to introduce today is essentially due to Bellissard from a good 20 or 30 years ago now, actually. But yeah, so with this topology that I've just defined, then this set of Delone sets is what's called a compact and metrizable space. So it's a good space. You can put a metric on it, though. Right. It's not necessarily easy to write down, but it's a nice topological space. Okay. So we can say a bit more. So about the set of Delone sets. So in particular, if you take a Delone set and you just do a rigid shift, so every point you just shift by some vector A, then clearly that's also going to be a Delone set because all I'm doing is just shifting things around rigidly. So, I mean, and actually this is also not just a nice shift, but it's also a nice homeomorphism of this topological space that we constructed. So it's continuous, has a continuous inverse. And now we want to, so here we're going to sort of bring in another assumption, which is about sort of essentially a choice of origin or something like that, because we're now going to just pick a Delone set, which I'll just to distinguish it from these L's, I'll call it lambda. And we want to study, okay, there are various properties that we want to study about this lambda, but at the very least, we would expect that it should not really depend on our choice of origin within this set. I mean, so if I have a point, it really shouldn't matter where I've chosen my origin. So if I take my lambda and I choose a point X in lambda to be the origin, so I do this shift here, which will just move X to the origin, then they should be more or less give me the same properties as this original set, lambda. But you have a problem, right? Because this set lambda is not doesn't have to be periodic, and often is not. So as sets, I do not have this shifted lambda is not the same as our original lambda. So I've actually gone to a different set. So how do you resolve this? Well, one way to do this is, rather than have just a single Delone set lambda, we consider a collection or a family. So I define this new space omega, which is going to be just the set. So I take all the points in lambda, which I've then shifted to the origin, that I take that collection. And then I need, just for convenience, well, because it's a useful thing to do, I then take the closure of this set within the space, within this topology that I just defined. So I get a nice closed subset of the set of Delone sets. So again, it's compact. So we get this set omega from our choice of lambda, and in particular, so every element within the set omega is going to be the Delone set, and the origin is also going to be an element of L for any set within omega, just sort of by the way we've constructed it. Okay, so with these points in mind, so okay, we have a Delone set and we take this family, then we get what I think is quite a nice sort of algebraic structure out of this, which is encoded in this sort of curly G here. So this is going to be a pair of points. So we take an element L within omega and then X within just RD, but such that X is in our point. So Delone set and elements within that set. So from this G, I get a bunch of structure actually. So first I get two maps, a so-called range map and a source map. So the range map, okay, they should take values in this what's called this transversal set omega. So one is just, okay, just project and take the L. The other one is shift the L by the point X, and sort of by the way that omega is constructed, this L minus X is also within omega. So I have these maps. These are actually local homeomorphisms, but that's not so important. So I also have a so-called partially defined multiplication. So unlike, for example, a group where you can multiply any two elements, I can multiply sometimes, but not all the time. So if I have L and X, and then L minus XY, so in particular, the range of this guy is the source of this guy. So, okay, what does this mean, right? So if I have this point here, then this is telling me that Y is in L minus X. So in particular, just rearranging this, says that X plus Y is in L. So as such, I get another element, L X plus Y. So I have a sort of a basic notion of multiplication, or in this case, kind of more addition, if you like, but it's only partially defined. So it needs to have sort of this type of form where these two points line up. And also I can take an inverse. So the inverse of Lx is sort of L minus X minus X. And you can also check that this is an element within G. Oops. So when you have such a structure, sort of partially defined multiplication, inverse, and these range and source maps, then this is what's called a groupoid, which I won't go into really details about, but it's a nice mathematical structure which you can just purely just study these guys and you have lots of interesting examples. So in particular, all groups are groupoids, all sets are groupoids. You have lots of examples. So what are some examples of these Delone type groupoids? So let's just first consider the case where you have the simple periodic set. So you'll lattice is actually just the usual integer type lattice. So if we were to build this set omega, then we look at points of this set ZD and then minus X, where X is in ZD. But of course, if I shift the integers by an integer, then I still just get the integers. So I don't actually get any new sets here. So this space omega is just going to be a single element of the set ZD. So it's just a point. And in particular, this curly G, this groupoid, is now just going to give me back ZD, but now actually as a group, because this multiplication will be the multiplication of ZD as a group. Similarly, if you can take a space group, which if you know what that is, then it's like this, but a little bit more complicated. Then this set will just be finite. But when you have these non-periodic examples, so for example, you have a quasicrystal, then this set omega is a Cantor set, which hopefully some people have heard of. It's this sort of nowhere dense closed set where you get it by sort of removing, you take an interval and you take out the thirds and sort of iterate that process. If your set is amorphous, then we don't really, in general, we can't really say much about what this set is, but in some sense it doesn't matter, because we can just study this groupoid G and we still get lots of nice properties regardless of how periodic or aperiodic our initial set was. Okay, so maybe just to spend one more minute talking about a quick application of this. So there's lots of different things you can do with this groupoid. So you could study tilings, you could study more mechanical properties, but I want to just quickly talk about sort of topological properties coming from physics. So again, take a Delone set, and now let's think about this Hilbert space of just sort of the square summable sequences of this set, and just sort of write down the most simple Hamiltonian that you can think of. So what we do is for points X and Y and L, we just couple these 2 points, and then we just have it so that they have exponential decay with some coupling constant. And we also add a magnetic field term, but you can ignore this if you like, it's not so important. And again, so rather than considering a single Hamiltonian HL, we consider the family for sort of similar reasons as what I explained before. And so this family gives you a single element H. And this element H, or little h, is an element in this object here called C star G theta. And this is a thing called a groupoid C star algebra. There's a twist, but again, don't worry about it too much. And what's useful about this construction, I'm not going to really explain what C star algebras or groupoid C star algebras are, but if you have something here, then there is a nice homology theory of C star algebras, which sort of extracts topological information about this element. So I have in particular these so-called K-theory groups, where very roughly speaking, the elements of these K-theory groups describe the so-called topological phases of this Hamiltonian. So, okay, this is a bit specialized, but people like Jinkai and others study these guys. And so you can ask analogous questions about Chern numbers, the bulk boundary correspondence, and these sort of properties coming from topological insulators and superconductors, but now on quite general sets. So just Delone sets, amorphous, quasicrystalline. And these are the sorts of things that you can do. This is, an application, but there are others as well. But yeah, that's all I had to say. So thanks very much. I'll stop there.
Thank you very much, Chris. Very clear and very inspiring talk. So is there any questions from audience? Raise your hand if you have, or unmute yourself. Okay, so Jinkai, go ahead.
Okay, thanks for a nice talk. So I just wondering, is this Delone set correspond to like every space group? Like in 3D, you have 230 space group, and
yeah, so a space group would be an example of a Delone set, but it's also true if you look at this G here that you would build from a space group, it would not have all the extra sort of point group structure that a usual space group has. So a space group, you know, it has this nice extra structure that you have G and then divided by ZD, you get some point group. You're not going to see that if you just look at this groupoid here. You have to then by hand sort of put in this extra structure. But I mean, you still could. It's just that would be extra information.
I see. And next question is so once you have this Delone set, you can go to like a C-star algebra and classify the topological phases.
Right. That's the basic idea anyway. Yeah.
So basically, the connection is like if we in condensed matter we have a 230 space group, then you really can connect to your classification. Is that right?
So again, if you wanted to look at, in particular, space groups, then, I mean, you would need more than just this information here. You would also need, for each space group, for example, the information, how the point group acts on the lattice and this extra structure. I mean, you can put this in, but it's going to be extra work that you have to do. And in particular,
I see.
But it's also true that, so yeah, calculating this group is also actually quite hard in the space group case, or also in the general case as well. But you at least know it exists.
I see. Okay, that's interesting. Maybe we can talk more later.
Sure.
Thank you.
Okay, so next, Hatsuda-san.
So you picked up X from this RD, but can it be changed, say sphere or torus? So I mean, does it matter or it doesn't matter in this structure?
I mean, it probably doesn't. I mean, you could, for example, also consider the hyperbolic plane or something like that. I guess if you had a compact manifold or something like that, and you had points on it, then you would just have a finite set. And I wonder if maybe you would lose, maybe the fact that I think the fact that it's infinite also sometimes helps a little bit. I mean, I haven't thought about it too much, but presumably you could play a similar game where you have a torus or something like that, and you look at points on this torus, and there's some kind of rough, almost like a triangulation or something like that. But yeah, I'm not sure.
Right, thank you.
Okay, so next, Nakamura-san.
Yes. So your parameter d, small d dimension can be any integer. You can construct the model, yes, for any kind of integer.
I mean, so if, for example, this very basic Hamiltonian, yeah, I mean, it can be 1D, 2D, 17 dimensions. It doesn't really matter. But I mean, it's also true, though, that, you know, for example, if you're interested in studying, for example, these topological phases, then just from this Hamiltonian, okay, it's very easy to write down, but actually solving it is, for a general random set, is very, very hard, right? At best, I think you probably just have to do numerical approximations, which I've seen it done in 2D, but I think that's the only one I've seen.
For very large D, do you have any interesting physical model? Or?
I mean, yeah, I don't think I have any sort of Well, I'm not sure any sort of new phenomena pops up in higher D that maybe is not also there in low D as well. I mean, in particular, I mean, if you are happy with this model, then it's not, I think a lot of the properties, well, there's nothing extra that you get by being in very high dimensions that you would not already see in low dimensions, but there may be others. I just haven't thought about it.
Okay, thank you.
Okay, thank you very much. Okay, Iritani-san, maybe last question.
Yeah, thanks for the great talk. And I'm curious about, so when you mentioned the quasi-crystal case, the Delone power set is homogeneous to a homomorphism to Cantor set, right?
Right, yes.
And is it, so if I call this, transformation forward, is it possible to think backward? Like if you give some set and try to realize some, physical structure like crystal or lattice or something. You see what I mean?
I mean, maybe, but I think in particular for a Cantor set, it's a bit too general because a lot of things actually turn out. If you have a topological space, it's surprising how many are isomorphic to a Cantor set. So you can get a Cantor set from many different starting points. You always seem to finish at a Cantor set. So in some sense, going back is then going to be hard because you could have gotten this Cantor set from an entirely different perspective, but it might still be useful. And I mean, there's a lot of research about like looking at dynamics of Cantor sets, and
right.
I think some people have also tried to say, okay, what does this also mean for quasi-crystals and these sorts of materials? But yeah, I don't know how much has been done.
Okay, great, thanks.
Okay, thank you very much. And many of you may have questions, and actually I have some questions, but let's thank Chris again and just close this 15 minutes talk. Thank you very much, Chris. Okay, so